Hello and welcome to the 11th of our NASA Engineering and Safety Center Guidance, Navigation, and Control webcasts. I'm Neil Dunn, the NASA Technical Fellow for Guidance, Navigation, and Control, and I'll be your moderator for today's webcast. As I have previously mentioned, the idea to have these hour-long webcasts originated with the members of my NESC GNC technical discipline team, who thought they would be a good way to broadly share their individual knowledge with the rest of the NASA GNC community of practice. We are nominally holding these GNC webcasts on the third Wednesday of every other month at this same time, 2 p.m. Eastern. Please note that the webcast is being recorded and will be made available for subsequent viewing on the NESC Academy site. I'm now very pleased to introduce today's speaker, Dr. Chris Tuzza from the Johnson Space Center. Chris received his BS and MS degrees in Aerospace Engineering at the University of Illinois, Urbana-Champaign, and his PhD in Aerospace Engineering from the University of Texas at Austin. He began his career at the Jet Propulsion Laboratory working on the Magellan mission to Venus. He has also worked at the Draper Laboratory, specializing in autonomous rendezvous and docking, linear covariance analysis, pseudospectral methods for trajectory optimization, and optimal guidance laws. Since 2005, Chris has been with the Johnson Space Center, first working on the Orion navigation, guidance, and targeting design for both rendezvous and cislunar operations. He is currently the Deputy Chief of the GNC Autonomous Flight Systems Branch. His interests include optimal guidance laws, optical navigation for rendezvous and cislunar flight, and trajectory optimization. The complete version of Chris's bio is available on the webcast registration site for your reference. Chris's talk today is entitled Fundamentals of Kalman Filtering and Estimation, and he will be giving us an overview of that subject area. Just as an aside, some of you may recall Professor John Crescides conducted a webcast back on the 16th of January, providing an overview of attitude determination and estimation. That talk is very complementary to the topic that Chris will be addressing today. So if you are interested in this topic of estimation, you should plan on visiting the NESC Academy site, where John's recorded webcast from this past January will soon be posted. And now I'd like to turn this webcast over to Chris, and I hope that you find his talk informative.
Thanks a lot, Neil. I hope we all enjoy this next hour together. My name is Chris, and I just want to begin by giving you a little bit of background. And the first question to be asked is, why do we want to estimate? Well, we estimate without even being conscious of it. Anytime you walk down the hallway, you're pretty much estimating, because your eyes and your ears and your proprioceptive system are the sensors, and your brain is the computer. So in its essence, estimation is nothing more than taking noisy sensor data, in this case your eyes and your ears, hopefully not too much noise, filtering the noise and producing the best state of the vehicle. In this case, it's you. But as NASA engineers, we actually estimate a variety of things. For navigation, we estimate position, velocity, attitude. Sometimes we estimate mass and sometimes temperature. A lot of times we estimate our sensor biases. And the quantities that we estimate are usually referred to as the states of the system. Now, we use a variety of sensors to accomplish this task. For example, we use inertial measurement units, we use GPS receivers, we use LiDARs and cameras. I'm going to be spending a little bit more time talking about each of those in a few minutes. And obviously these sensors are used to determine the states of the system. Now, it turns out that estimation has its origins in the work of Gauss, and he invented something called the least squares estimation. As a lot of the mathematicians and the engineers of that era, he was interested in computing the orbits of asteroids and comets and planets, given a set of observations. And since Gauss, much of the work through World War II actually centered around extensions to least squares estimation, because that was kind of the hammer they had, and everything looked like a nail. In between World War I and World War II, a number of concepts, in fact revolutionary concepts, were invented, and specifically with regard to sampling and estimation theory. Norbert Wiener at MIT came up with what was subsequently called the Wiener filter. Claude Shannon, as well, who was an electrical engineer, invented what we now call sampling theory. And so much of the work in the first half of the 20th century focused on basically analog circuitry and the frequency domain. And that stayed until the confluence of two events, specifically the Cold War and the space race. The second thing that happened was the advent of the digital computer and semiconductors, and all of this was in the mid-40s to early 60s. And during that time, a new paradigm was introduced, specifically called state space analysis. And part of the state space analysis paradigm was it did involve linear systems and modern control theory. In particular, estimation theory and optimization theory, which originally was the purview of mathematicians, now became the purview of engineers. At that time, in about late 50s, Rudolf Kalman, who was a Hungarian immigrant, proposed a new system, a new approach to linear systems. Specifically, he invented this concept called controllability and observability. It turns out in 1960, after he got his PhD from Columbia, he wrote a paper in an obscure journal, the American Society of Mechanical Engineers. It was entitled "A New Approach to Linear Filtering and Prediction Problems." Turns out that he was not an easy person to get along with, and he made a lot of people in the IEEE community mad, and so he had to go to the ASME. And so he published this paper there, and it might have died in the vine, except in '61, Stanley Schmidt of NASA Ames read the paper, and he invited Kalman to give a seminar at Ames. Schmidt was the first one to recognize the importance of this theory, and he applied it to the problem of navigating a lunar vehicle to and from the moon, because this was the beginning of the Apollo program after Kennedy's announcement. And Schmidt started calling it the Kalman Filter. Well, it turns out Kalman's filter, if you even read it today, is rather obtuse in its nomenclature, and Schmidt transcribed it for engineers, and he showed that it could be easily mechanized, and he applied it to a real problem. In fact, the Kalman filter became the basis of the onboard navigation filter for the Apollo lunar and service module. So there are basically two types of estimation: batch and sequential. Batch estimation is when we take a set of measurements over a period of time, a large period of time, and we batch them together, and we group them together, and we process all of that together to estimate the state of a vehicle at a particular epoch. This is usually done in the case of ground navigation processors. The alternative is what's called sequential estimation, in which measurements are processed as they're taken, and the state of the vehicle is updated as the measurements are processed. And this is done in onboard navigation systems, onboard vehicles. So what kinds of sensors? Well, we got IMUs, usually, on vehicles. In fact, mostly. We got GPS receivers. We got magnetometers. We got a whole slew of optical sensors that are available: visible cameras, IR cameras, LiDARs, both scanning and flash. RF sensors, radar, different bands of radar. We got range and range rate from COM altimeters and Doppler velocimeters. Those are just the sum of the concepts. So I wanted to talk a little bit about probability theory, because that's kind of at the heart. So what is probability? Well, I like this quote from Claude Shannon. It's the negative reciprocal of probability, which is information. So basically, probability is a measure of how much we don't know. It's a measure of our ignorance. And so what is a random variable? Well, a random variable is one whose value is subject to variations due to chance or randomness. It doesn't have a fixed value. It varies, right? It can be discrete or continuous. A coin toss is discrete. A light bulb is continuous. So how do we express probability mathematically? Well, we do it in terms of what's called a probability density function, which actually represents the likelihood that X occurs. So the probability density function is always negative, always non-negative, sorry. It satisfies that integral, meaning over all the possibilities, the integral sums to 1. And with that, we define what's called the expectation operator, and it's simply described as f of x. So the expectation of f of x is the integral of f times the probability density summed over all of the all values of x. So we also define what's called a mean. A mean is just defined as the expected value of x, and we're used to means, right? The mean, when you take a test, you want to know what the mean score is, and so that's basically, we're used to means. Something we may not be as used to is called the mean squared, which is just defined as the expectation of x squared. And then finally, we've got what's called a variance, and the square root of variance is called the standard deviation. We're used to that concept as well, and that's also called the second moment, and it's just defined as the expected value of x minus the mean of x squared, and it's related to the mean squared in the bottom equation. Now, that was for scalars. What about for vectors? Well, vectors, operate in the same way. So the expected value of a vector is just the expected value of x, or the integral of x times the probability over all types over the vector x. Similarly, the covariance of a random n vector is defined in terms of the equations there, and that matrix is often called the covariance matrix, and geometrically it's represented in terms of what's called an error ellipsoid. It's an ellipsoid in n space. So one of the other things in probability theory is a thing called the Gaussian distribution, which is also called the normal distribution or the bell curve. And it turns out that this is actually the heart of Kalman filtering, and those of us who do this sort of thing, we like Gaussians because we can understand them, we can express them mathematically, and they're actually nice functions to have. And I like this quote by George Lippmann. Everyone believes in the normal approximation of the Gaussian. Experimenters think it's a mathematical theorem, and mathematicians think it's an experimental fact. So everybody likes it. And we will assume that our random variables have Gaussian probability density functions. And so we like to work with the Gaussians because they're completely characterized by their mean and their covariance. And it turns out that linear combinations of Gaussian are also Gaussian, and that's really nice. So what's a Gaussian? Well, a Gaussian is, in terms of that equation, it's an exponential involving the mean and the covariance, and specifically in the exponential, it's the inverse of the covariance, and that's really nice. So here is our normal Gaussian. It's a bell curve, right? Its center is around the mean, and then it's got a particular variance, and it turns out the variance is at the inflection point. So it's that's how you locate where the variance is. And we can show that this integral is equal to 1. And I like the quote from Lord Kelvin, and he said, well, a mathematician is one which that integral is as obvious as 1 + 1 = 2. Now, to most of us, and me included, it's not that obvious. And I guess by that definition, I'm not a mathematician. I'm an engineer. I have to actually work that guy out. And along with that is if you have a whole bunch of random processes, which are non-Gaussian, then in the limit, if you combine enough of them, guess what? You get a Gaussian distribution. And that's what's great about it. So now that we're done with probability theory, let's talk about linear systems. Well, what's a linear system? Well, first let's talk about what a system is. A system is nothing more than a mapping from input to output. And we usually write it in terms of L of V, where V is the input. A system is linear if for all signals. It satisfies the additive property, and it satisfies the homogeneity property in terms of the scalar alpha. So what does that mean for us? Well, for a system to be linear, one of the important properties is that if 0 is an input, then 0 is an output. So if a system does not satisfy those properties, it is nonlinear. So the question for us is, what about that function? L is equal to V plus 1. Is this linear? Well, sure looks linear, doesn't it? Well, it's not. Because for V equals 0, guess what? L of 0 is equal to 1. It's not equal to 0. Therefore, it's not linear. So what's the lesson? Well, the lesson is, well, some systems may look linear, but turns out they're not. So be careful. So despite the beauty associated with linear systems, the fact of the matter is that we live in a nonlinear world, don't we? So what do we do? Well, my one of my favorite phrases is that if you have a hammer, everything looks like a nail. And so we make these nonlinear systems look like linear systems by a process called linearization or linearizing. And so what linearization is nothing more than a Taylor series approximation, which we deploy as follows. So we're given a nonlinear system in terms of x dot, some sort of mathematical law, Newton's law, for example. So we linearize, or we expand about a nominal trajectory, call it x star. And so we perform a Taylor series. And that's all we do. We're just expanding a nonlinear system in terms of a Taylor series. And after all of that is done, you get a linear system. Pretty cool, huh? Well, so if we do that, guess what? This fancy nonlinear system just becomes something like x dot equals f times x. And guess what? That's a linear system, and we know what to do with that. So it turns out that the solution of that guy is nothing more than that integral, the exponent of the integral. And I know I'm reaching way back to first-order differential equations on our diffie-q class. Well, all that is just the homogeneous system, and or the homogeneous solution. And it turns out that that exponent is nothing more than what we call the state transition matrix. In the state transition matrix, if you actually differentiate that x dot equals the integral e to the f whatever, it turns out that that is phi dot equals f of t, f times phi. Well, on the surface, it doesn't seem like we've really done anything. We've actually converted a vector system into a matrix system, and that's not very good. But it turns out that we can approximate the state transition matrix. And we can approximate it as follows. So given x dot equals f, which in this case f is a constant, we get I equals f, I plus f times delta t plus 1/2 f squared times delta t squared, on and on and on. And the reason I'm making so much hay over this is that we use state transition matrices a great deal. And so the state transition matrix, as it turns out, is at the heart of practical Kalman filter. And what it is nothing more than transitioning a state. It's a partial. And so, gosh, all it is we, given a perturbation at one time, you use the state transition matrix to move it to another time. You push it along. You transition it along. And so that's what that is doing. And it's nothing more than what you would expect, right? And so in practical Kalman filtering, what we do is, we use a first-order approximation. And all it is I plus f times delta t. And that's what we use in Kalman filters usually. And in certain cases where we've got fast dynamics, we may carry it out as second order. But that's unusual. So that's done with the background. Let's actually start some estimation. Well, I love John Archibald Wheeler's first moral principle. Never do a calculation unless you already know the answer. And in case you don't know who he is, he was one of the physicists who worked on the Manhattan Project, and he was one of the people who came up with the concept of a black hole and quantum tunneling and all of those sorts of things. But he was one who always wanted to know the answer before he knew the answer. So in the context, we want to talk about least squares estimation, and it's been a mainstay of engineering and science since Gauss invented it to track the asteroid series around 1794. And it's been used, and it has been, and it is, and it will be used as the basis of ground-based nav systems. And the Apollo program had an extensive network of ground stations, and they processed it using least squares estimation using batch processes. So then they got all of these measurements over several orbits, and they batched them together and got a state at a particular epoch. And what least squares estimation does is, all it is it's predicated on finding a solution, which minimizes the square of the errors. And the errors in this case are basically epsilon. So you've got a set of measurements, y, a state x, and some sort of mapping between the state and the measurements, corrupted by errors. And you want to find the best state that minimizes epsilon. So basically what we do is, given a set of measurements, y, we want to minimize the measurement error. Well, how do we do that? We do the least squares. So we find the square, we find the best solution which gives us the least error, the least squares. And so what we do is, since we have a vector set of measurements, we do 1/2, and 1/2 is just there for computational ease. it really doesn't matter. It can be a fourth or a 200th or whatever. And so what we're doing is we're finding the best x given a set of y that minimizes that function. And what do we do in order to minimize? Well, from first semester calculus, take derivatives. Well, in this case, we've got vectors, so we got to be a little bit careful, but not much. And we want to find the best x that does that, and we call that x hat. And so after all is said and done, it turns out that the optimal solution x hat is nothing more than that function. It's just h transpose h. You take the inverse of it, h transpose y. And that's the best solution. That's the best least square solution. Okay, that's good. Let's make it a little bit more complicated. Suppose we're given a set of measurements so that we have a measurement error, and we know what the statistical properties of that measurement error are, and we call it R. How can we get the best estimate that minimizes the errors weighted? So, for example, if you have a very accurate set of measurements, R would be small, R inverse would be large, so you weight it large. So basically, you're just doing that function. And now you just turn the crank. Take the derivative, set it equal to 0, and guess what? You get the same sort of thing as before, except you get this R inverse thing floating around. So basically, in this particular case, you got two inverses. You got R inverse, and then you got H R inverse, H quantity inverse. But suppose we're given an a priori estimate of the state, X bar, with covariance P bar. Well, what do? Well, we create that performance index, that functional. And once again, we turn the crank. Well, take the derivative with respect to x, set it equal to 0, and pop, out comes x hat. Now, it's a little bit more complicated, right? You got this p-bar inverse stuff. And but in general, we don't work in a linear world. We work in a nonlinear world, right? We got nonlinear measurements. Range, for example, is not linear in terms of position. How do we get the best solution of x? So what do we do when we have a nonlinear system? Well, we linearize. We pull out our hammer and we linearize. So just expand in the Taylor series, and we expand to first order. And if we define h tilde as that partial of h respect to x, and a little y as y minus hx, guess what? We get this solution, which looks surprisingly like what we had before. So once again, if you have a hammer, everything's like a nail, right? So we're using our linearization hammer here. But in reality, remember I said when we talked about batch estimation, we were interested in estimating not at each x, but at a particular epoch, say x0. Well, what do? Well, now we use our paradigm of the state transition matrix. Now we push our state estimate from tk to t0. So we use a state transition matrix. So we map everything back to our epoch of interest, in this case x0. And so then we create this thing y equals hx 0 plus epsilon. Looks surprisingly like we had what we had before, right? And so it turns out that the least square solution for over all measurements, now we're summing over all measurements, is nothing more than what's in that fancy equation there. And it turns out that this is a very important equation, and so it's given a name. It's called the normal equation. I don't know why it's called the normal equation, but there it is. So what's the algorithm? Well, I don't know if you can see it very well. Basically what we're doing is we got an initial estimate, we're reading the next observation, we're computing your state transition matrix, computing the partials, and computing all of these quantities such that you can invert. And then what you do is you keep doing this loop, and then finally after you're done reading all the measurements, then you actually perform the inversion. Well, we got a nonlinear system, right? So it's not going to converge initially. So we got to iterate, and that's what that if-then loop is all about. Well, so let's do an example. Given a ground tracking station, and we got an airplane moving in a straight line at a constant speed, we only are able to get bearing measurements. For example, maybe the range portion, the range aspect of our tracking station is disabled, and we only know the bearing. So given that, can we determine what the position and velocity of the airplane is at the initial at the beginning of the path? Well, the equations, everything's in a straight line, right? So there's your equation for x, and there's your equation for y, which is the altitude, and there's theta. That's the measurement, right? It's just the arctangent of y over x. Not very hard. Well, it turns out that here are the measurements that I'm given. There's noise in the measurements. I'm given 10 measurements every 20 seconds, and the angle is changing over time, corrupted by noise. And I'm given an initial guess, something like that. I don't know what it really is, and I'm trying to find what the actual position is with some covariance. I've got 100 feet error in position, actually 10 feet error in position, and 1 foot per second in velocity. And so what do? Well, I crank through my algorithm. And guess what? After 7 iterations, I'm telling you what the truth is there. I've also stated what the initial guess is. And guess what? Here's the solution. Well, I'm doing really good in Y0, U0, and V0. But X, gosh, that hasn't moved very much. Well, there's a reason for that. The reason is that the X component is not readily observable. Well, we knew that because bearing, it doesn't give me any information along the line of sight. It gives me information orthogonal to it, and so I can observe all the other stuff. So I could iterate as many times as I want, up to 1 billion times, and it's still not going to improve my X position. It's going to nail my Y in U and V, but it's not going to help me in X. So what's the lesson? Well, the lesson is that one must watch convergence of numerical code as carefully as a father watching over his 4-year-old play near a busy road. So that's least squares. Let's talk about Kalman Filter. After all, that's what we're here for. So I love this quote by Migliori. 6 months in the lab can save you a day in the library. So let's spend a day in the library, and let's look at a first-order differential equation for x. So this should look familiar, right? Our first differential equation course in college, we were solving these kinds of equations. X dot equals f of t, x of t plus gw, right? And I know it's been a long time ago, for some more than others, but here is what the solution is. It's you did the homogeneous solution, and then you substitute back. You got a particular solution. I mean, this is what they did, right? This is the standard first-order differential equation, right? Well, suppose now we define that integral as phi. Well, it turns out that is a state transition matrix. So when you actually took your first-order differential, when you took your diff-EQ course, you were actually not knowing, but you're actually doing state transition matrices. And so there it is. There's that phi again. We really can't get away from it, can we? So now let's crank it up a notch. So given that we have a first-order stochastic, now it's random, with a constant f, ng, and white noise. It's driven by white noise. W, which was the input, is now white noise. And we're given some sort of x0 or chi0. And the mean of the noise is zero mean, and it's got some sort of strength. Delta there is a Dirac delta, for those of you who care. The mean of the process, well, there we go. We just plugged in what we had before. The expectation operator is a linear, so I can take it inside the integral. And guess what? The mean of W is 0, and so we just get e to the f t minus t0. So that's once again the state transition matrix. So the mean of the process just involves the state transition matrix. What about the mean squared? Well, the mean squared is that, and you can show it. I'm not going to do it. I don't have time to do it, but there it is. And likewise, the variance is that. It's pretty simple. It's kind of simple. So, excuse me. So anyway, now that we do a scalar case, let's do a vector case. Well, there it is. X dot equals fx plus gw. Once again, w is a noise. Got q. The solution of that equation, once again, it looks familiar, doesn't it? It's a state transition matrix. That is the first term is the homogeneous solution. The second term is the particular solution. It looks familiar. It's And so this is that's a solution of that particular equation. Well, turns out that phi, once again, satisfies phi dot equals F times phi, right? So we're back to the state transition matrix again. Seem to never get away from that one. And the mean of the stochastic process is just that. You're just taking the expected value through that, and it makes sense, right? The expected value at any time t is just the expected value of the initial time pushed by the state transition matrix. And the mean squared is that there. And I'm just going to move forward to the covariance. And the covariance is just phi p phi transpose plus that integral. And it's a messy integral, but we're going to get back to that guy in a minute. So just keep that in mind. It's just phi p phi transpose plus some sort of integral. Turns out that that integral, you can actually take the derivative of that equation above, and if you do it, you get the differential equation. P dot is equal to FP plus PF transpose plus GQG transpose. And remember, we said that Q, our noise is white and Gaussian, so it's white and stationary, and so Q is not a function of time. So basically, if I want to solve for P, I just look at the above equation. If I want to get the differential equation, there it is. And so if you guys know about Dirac deltas, what we'd like is Dirac delta, because that's the definition of Dirac delta. It's what it does to functions under integration, and this is a perfect example of that. So, but we tend to want to use a computer, so we usually like to discretize it. And so the solution, once again, I haven't said anything there. This is the normal equation that we had before. We've seen over and over again. I've just recast it slightly. And so the discrete analog is just x of time k is the state transition matrix, x k minus 1 plus w, and w is this integral. And so the first part of the equation looks very simple. And so the mean, once again, is just x of k minus 1 pushed forward by the state transition matrix. Likewise, the covariance, we had that integral I told you before. Well, turns out that it can be written in this form where q is that, but normally we don't work with the integral for q. We just use q, and we take it. And I'm going to talk about that in a second. So let's talk Kalman filtering. Well, Kalman filtering, there's nothing more practical than a good theory, and Kalman filtering is one of those. It's a great theory, and it's a great technique as well. So with the advent of the digital computer, the question was, can we recursively estimate the state of the vehicle as measurements become available? And the answer was yes, because Kalman came up with a methodology to compute the optimal state. And remember, since we have linear states and linear measurements, if we compute an optimal, we know that it's global because it's linear. So the Kalman filter is a globally optimal linear model-based. We're given a model, and it's driven by Gaussian white noise. And we got two steps. We got a propagation step in which the state and the covariance are propagated from one epoch to the other using those equations I stated before, followed by an update state, where given a measurement, we update both the state and covariance. And this is nothing more than a predictor and a corrector. The propagation is a predictor. The update is a corrector. So we begin with the same equation as we had before, right? Y equals hx plus epsilon. We're trying to find the best state which minimizes the errors. So what do? Well, like I said before, the Kalman filter is nothing more than a predictor, which is the propagation phase followed by a corrector. So we use the dynamics, in most cases Newton's law, to predict the state to the time of the measurement, and the measurements are used to correct. And this is done optimally. So what does that look like? Well, here's a picture. Given an initial state at time t1 with an initial uncertainty in that little ellipse, we propagate or we predict forward in time to t2. And the covariance is going to grow with time, and there is the uncertainty. Well, next we get a measurement, and it's got a certain uncertainty associated with it. right? So then what we do is we compute the residual, which is just the difference of the two. And from that difference, we obtain the corrected state. So we get a prediction and a corrected state. And then there's an uncertainty associated with the corrected state. And notice that the uncertainty is always smaller than the prediction. Okay? So that's fundamentally, geometrically, what we're doing. A prediction followed by a correction. Prediction, correction. So let's spend a few minutes kind of doing a derivation. So we've got some sort of a priori estimate xk minus with a covariance pk minus. We compute our error ek minus with covariance 0 mean. And we hypothesize that we want to have a linear update. So xk plus, the updated state, is something involving xk minus plus a gain times something. Okay? So xk plus, we can compute the a posteriori state, ek plus. And ek plus is nothing more than xk minus xk plus. And so we can compute that in terms of that equation there. And if ek and epsilon k are uncorrelated like they usually are, then the a posteriori covariance is nothing more than pk plus. And all it is expanding that above equation. But so far we haven't said anything about k, right? So now what we do is we choose k in order to minimize the error, in this case the a posteriori error. And what we do is we use some, so remember j is a scalar, and what we can do is we can use what's called the trace operator, where we just introduce a trace, because the trace of a scalar is a scalar, and then we manipulate the trace, and we can use what's called the cyclic invariance property of the trace, and all it is we're just rotating it until finally out pops the trace of the covariance matrix. And so what we do now is we substitute for pk plus from the equation on the previous page, which is there, and we just minimize with respect to k. Well, minimization of traces with respect to matrices is not something we just talked about very much, but nevertheless, there are the equations. And so what we get is the following condition, which gives the optimal gain. That is called the Kalman gain. And if we substitute for pk plus, you get this pk plus is equal to I minus k h pk minus. And the state update is now what we had before, but now we've actually computed what the optimal gain is. So what's the Kalman filter? Well, the Kalman filter is nothing more than given x, which is phi p x plus gamma, and a set of measurements. So we do what's called the propagation phase, which is xk minus and pk. So the covariance is increasing. Notice the plus sign there in that covariance term. And then we do an update in which the covariance decreases. We've got a gain and the other equation. And in this case, the covariance decreases. So let's do an example. Given a spring mass damper system, which is governed by the following equation, we can write it in terms of first order form, and you can write it in terms of the state transition matrix. That exponent is actually the state transition matrix. And here are the measurements. We're given, we measure y, and we're given the covariance, initial as well as process noise. Here is what the actual 100 runs of our position and velocity are. So you can see it's pretty noisy. And guess what? After we run our Kalman filter, this is what we get. This is the estimate error noise, or estimate error. And you can see it's very small. It's 0.15, and in the red is the sample covariance, and in the green it's the filter covariance is what it thinks the covariance is, and the red is actually the covariance. And you can see the two are very close, which tells me that my filter, I've got a well-tuned filter. So how do we do this in real life? Because we live in a non-linear world. Well, we actually compute, and we avoid the computation as much as possible, but now we got to do it. So how do we fit this paradigm into the real world? Well, we actually use linearization. So we take our nonlinear measurements and our nonlinear dynamics and we linearize. But when we do that, we lose any guarantees of stability and optimality. So here it is. Begin with a nonlinear system, and there's the solution of the nonlinear system. And we expand in a Taylor series. And we neglect higher order terms, and there's our covariance matrix. There it is, Fp plus Pf transpose plus Q. Look familiar, doesn't it? That's the same as the Kalman filter. And the solution is just Phi transpose plus Q. And there it is for phi again. Same stuff. And likewise, the measurements are done that way. And turns out that it looks exactly the same, almost exactly the same. But the difference is this common gain here is now a random variable because it's a function of x hat. So that's the difference. So here is the algorithm. Read the measurement, integrate the state, update the covariance, compute the measurement y, and compute the gain, and then update the state, and you do this recursively. This is the algorithm. It's very, very simple. So how do we implement it? Well, in theory, there's no difference between theory and practice, but in practice there is, and there is a lot of difference. Because in general, no more than one measurement will arrive at the same time. Usually the measurements are uncorrelated. And if they're uncorrelated, they can be processed one at a time. But even if they're not, you can treat them as being uncorrelated, just increasing the measurement variance slightly. So if they're processed one at a time, guess what? That matrix inversion there, it's a simple scalar division. So we don't have to worry about matrix inverses in our flight software. So we can greatly reduce the computational throughput. But in reality, our sensors aren't necessarily Gaussian, are they? I've never seen a Gaussian sensor yet. They're never Gaussian. They have significant biases. They've got significant third moments, significant kurtoses, and it turns out that a great deal of information is contained in the tail. And so significant sensor testing needs to be performed to fully characterize and determine its characteristics. And so what we do is we do measurement editing. And we do editing on the innovations process, which is nothing more than y minus h. It turns out that in textbooks and academia, they will usually just edit out measurements that are greater than 3 times the innovations variance, 3 times that v. And that works if everything is Gaussian, but it's not. And so what we like to do is actually we process measurements up to 6 times that, just so that we retain the information in the tails. And as well, measurements aren't polite as to be time tagged or arrive in the major cycle of a nav filter. So what we need to do is we need to process measurement at the time they're taken. And usually if they're greater than 3 seconds, we don't process them. But if they're less, what we do is we propagate the state back to the measurement time using a first-order integrator. And this should look familiar, right? Because that's exactly what we did in the batch. So once again, everything comes around. And sometimes you can get a very, very accurate measurement that's introduced to a state that isn't very accurate. And there are several ways to handle this. We can do second-order filters, we can do sigma point filters, or we can do something called measurement underweighting. And since Apollo, measurement underweighting has been used extensively. What underweighting does is it slows down the rate that the measurements decrease the covariance. Remember, in the earlier slide, I showed you that anytime you process a measurement, the covariance decreases. Well, sometimes it can decrease too fast, and so consequently, it causes problems. So we don't want it to decrease too fast. And so we do what's called underweighting. And basically, underweighting is nothing more than this factor alpha. So what we're doing is we're increasing that HPH transpose by a factor of alpha. We're inflating it, thereby increasing the covariance a little bit. And it turns out that that works really well. And so we use this alpha as a tuning parameter. So tuning. Regardless of how you slice it, tuning is an art. And I guess that's why navigators are so well paid. Oh, I'm kidding, actually. There are at least two sets of knobs one can tune. One can tune a filter. We have the process noise, also called state noise or plant noise, which is the noise in the dynamics, the measurement noise. So filter tuning, what is performed in the context of Monte Carlo. So you run a lot of simulations. And so what we do is we begin with the expected noise parameters. We begin with the process noise, what we expect the dynamics to be, and we also have measurement noise, and we begin with those. We also have what's called sensor parameters, zero mean Markov processes, which we model because our means and variances of the sensor aren't necessarily time invariant. So we model them as being time correlated. And so this is another parameter we use in order to tune the filter. So these are some additional knobs. And so all of these are tuned in a Monte Carlo environment so that the state error remains within 3 sigma bounds. I showed you that for a simple spring mass damper problem, didn't I? And so we tune it until the filter covariance represents the computed sample covariance. And finally, sometimes the filter designer will inadvertently choose a process noise which is too small, such that the covariance gets too small. And when this happens, the filter gets what we call it's smug. It thinks it's very sure of itself. And the end result is that the filter starts with rejecting measurements, which is never a good thing. So the solution is to inject enough process noise to keep the filter open. And this allows filters to process measurements appropriately. And this is just not a figment of my imagination, because there are several spacecraft that experience exactly these kinds of problems because the designers have chosen incorrect process noise. And this is nothing more than the tension between stability and performance. And once again, because we are in a nonlinear world, the order is important. And so sometimes if you processing range and bearing, the order in which you process it can be important. So what we do is on Orion, we employ what's called a hybrid linear filter, in which the state and covariance updates are accumulated in delta states. And then finally, when all the measurements are processed at a particular time, we update it. So this is basically Kalman filtering. And if we had additional time, we can talk about the Kalman-Busey filter, the Schmidt-Kalman consider filter, smoothers, square root matrix, factorization techniques. The Potter was used in Apollo, and Orion we use UDU. And there are all kinds of nonlinear filters, second order filters, sigma point filters, particle filters, entropy-based filters, all those sorts of things. And finally, there's also an important area called linear covariance analysis. None of these I've touched on, but we, if you're interested, I can broach those subjects one-on-one. So in conclusion, Kalman filtering and least squares estimation are at the heart of spacecraft nav, both ground-based and on-board. So its purpose is to obtain the best state of the vehicle given a set of measurements and subject to computational constraints of flight software. So as you have seen, I'm sure, it requires fluency with several disciplines within engineering and mathematics, statistics, and, numerics, linearity, nonlinearity, sensor hardware. A lot of challenges, right? Throughput, a lot of image-based constraints. So, to put things in perspective, I love this quote by Seymour Cray. Never want to be a pioneer. It's always best to come in second when you can look at all the mistakes. And in many ways, we are standing on the shoulders of giants. So, questions?
Hey, well, thank you very much, Chris, for sharing your knowledge and insights into Kalman filtering. I think if we put all those quotes you have together, you have a real philosophy for life there. Those are some intriguing quotes. Hey, we do have one question I want to run by you to start with, and that is, how about recommending a good Kalman filtering reference book that would complement the material you shared with us here today? Is there something you can, something that comes to mind?
Yes, John Junkins and I believe John Chrysitis have written a book called Optimal Estimation in Dynamic Systems, or something to that effect, and that's very good. There's
I was thinking the book by Gelb. It's a little dated, from '74. Applied Optimal Estimation.
Yeah, Gelb is very good.
It's a good book.
I find it a little bit hard to read just because of the typeface, but it's got a lot of good stuff in there, and GELB is very good. Then if people are interested in the OD aspect, the orbit determination aspect, the batch filtering aspects, Tapley, Schutz, and Bourne have got a very good book out there that focuses primarily on that. So there's a lot of good stuff out there, and I can direct people to different books depending on their application.
Okay, well, maybe I could impose on you. Maybe before we post up this set of view graphs, maybe you could add maybe one more view graph with the two or three references that you recommend.
Sure.
Would that be all right? That way we capture it as part of this this presentation.
Sure.
Okay, I guess one other question came up with, and a person is talking about. You mentioned underweighting, right?
Correct.
In the Kalman filtering, and you talked about using the scalar alpha. A couple things here. Are there any? You said it's an art, and I can certainly appreciate that, and see art of the navigators, right? And that is why you're so highly compensated, right? Anyhow,
like that.
Are there any rules of thumb you can share with us now here in real time, or you maybe think about it? But over the years, we must have accumulated some best practices, or do's and don'ts. Avoid these pitfalls. So when people go into that area, do they have? Is there some guidance you could share with folks in that area in particular?
Certainly, with regard to measurement underweighting, we have found that the factor for alpha of 0.1 is a good one to start at. So, okay. Sometimes, for Orion, sometimes we've actually increased it to 2. But we've started at 0.1, and that usually 99% of the time that usually works pretty well. So that's an easy one. Start at 0.1 and go north of that.
Okay.
So I've got some other techniques. There's Bill Lear here at JSC actually came up with this technique, and Renato Zanetti and Bob Bishop wrote an excellent paper in terms of actually picking that number. So there's some good information out there.
Maybe if you think it's something that would be a good reference, maybe you could add that to your list of a short list of key references, so we capture this for posterity. Let's see, we have a few more minutes here, I think. We have more questions, so this is good. So this question comes from Dan Yuknovich at Langley, and it concerns update time. I think what he's talking about, update rate of the filter, I guess how fast you run your filter. So the question goes like this: does the update rate help the accuracy of the estimate in a nonlinear system where only the first order term of the Taylor series expansion is used? Maybe I'll stop there. There's some more after that. Does that make sense to you?
Yeah. So you want to run the filter at the fastest rate that your dynamics are operating. So, for example, if your IMU data is coming in at 50 hertz, you want to run certainly the propagation at 50 hertz. Now, the update, you want to do that whenever measurements come available. But sometimes, I can tell you our experience in Orion, we run the propagation phase, if you will, at about 40 hertz, and the update is at 1 hertz. So if measurements come in that 1 hertz cycle, we'll usually map the state back to the measurement time and do an update. We're updating at 1 hertz.
There's a distinction here, I think, that you just made for us. It's the difference between the propagation rate and then the filter update rate, right?
Right.
That you've been talking about.
I kind of skated over that because some of that is kind of implementation, and it has to do with the constraints of flight software and what the different rate groups are, because usually from flight software you've got rate groups and things like that. So, and for example, flight control may need something coming at 40 hertz. You want to run your filter. If flight control is getting information from your filter, you want to run it at a rate that flight control is getting the appropriate information without too much of a latency. So a lot of those I kind of skated by just because there are a lot of subtleties there.
Yes, clearly a lot of subtleties. I think you answered one of Dan's other questions here about in the case where you do have an IMU, let's say, and it's outputting delta theta and delta V at 50 hertz, perhaps. you're certainly not going to run your Kalman filter at that rate. You might propagate at that rate, but you wouldn't be trying to probably update at that frequency. That's at least the takeaway I get from no advantage.
Need to update it, right?
And it's a burden too, like you say, on the processing system. Right.
You want to be as smart as possible, and there's always demands on computation within a flight processor. So you want to be as low footprint as possible.
Makes a lot of sense. Let's see. I think we may have one other question here. Oh, well, someone has asked a question about how to get the copy of the slides. I believe, as usual, the slides that you presented today, Chris, will be they'll be part of the package that gets uploaded onto the NESC Academy site, along with the video of your webcast here. So we'll have both. In fact, that is the webcast. When you cycle through the slides, we see the slides, and we have your commentary on top of that, which is nice. So I got a question for you here. Kurtosis, that's the fourth moment that it sounds like something you should see a doctor for, but
yeah.
How often is that used, and how is it used? Is it is it a useful diagnostic parameter, or how would you?
It is. It's so, for example, when you test a sensor, one of the things that is assumed in a filter is that it's Gaussian. And Gaussian processes have particular kurtoses which are related to the covariance. Turns out that sensors aren't Gaussian, and so it's got significant tails, and a lot of the information of how thick the tails are is actually contained in the kurtoses. Oh. And if it's skewed, for example, means that the mean, imagine your bell curve and somebody pushing at the tip of it, so it's kind of skewed. And on Orion, for the LiDAR that we were looking at, it had significant skewnesses in kurtoses, so we weren't able to, initially it didn't make, what we're seeing didn't make a whole lot of sense until we accounted for that. And so the end result is you can't do a whole lot about it, but you can increase your measurement noise to account for that. And so so it's useful information to have, so that when you're tuning your filter, you're not being naive.
Excellent. That's probably the best answer I've ever heard of. You're not the first one I've asked about that. So it's a way to get smarter about the nature of your individual sensor noise, maybe, exactly. And then it gives you some informed guidance as to how to tweak some of those covariance numbers and things commensurately, it sounds like.
Exactly.
So it's very good. Yeah. Okay. Well, we do have a few more questions, but I think we've run out of time. I want to thank you for answering those questions, Chris. I also want to thank you. I think what we'll do is pass on these remaining questions to you, and I believe you've agreed to answer them and send them off to send a response back to the people that submitted them. But sorry we ran out of time, but we do try to keep this to within the hour format, respecting other people's schedule. We are planning the rest of our program of future webcasts. We're trying to adjust topics of general interest to the GNC community practice. So two things. If you have ideas for other GNC webcast topics that you think should be addressed, or even better, if you yourself are interested in presenting a GNC webcast because you're a subject matter expert in a certain area, please contact me directly, and we'll try to accommodate that. With that, we've completed today's NESC GNC webcast. Thank you again, Chris. This was really good. I really appreciate you taking the time to pull it together and be with us today. I want to thank our audience for tuning in and participating with us, and I look forward to all of you joining us again in May for our next GNC webcast event. Thank you.